Welcome back to the Gas Compression Podcast. I'm joined again by Jim Dettore. He's the president and owner of FAS Training Services, Failure Analysis Services. And we've had a couple of podcasts where we've been talking about different types of wear. And today we're talking about corrosion. And so just a quick plug for Jim and what he's doing. If you're not subscribing to the Gas Compression Magazine, you need to do that. And Jim's writing an article in there every month now called What Went Wrong. So kind of taking a look at different applications in the industry and failures and what happened and what to do to prevent them. So if you're not subscribing to the Gas Compression Magazine, you need to do that and check out those articles that Jim's doing. So Jim, welcome back to the show, and glad to have you back.
Thanks, Michael. Glad to be back.
So we're
Looking
talking
forward to it.
corrosion.
We are.
Yeah, so it's another type of wear. We've talked about adhesive wear and abrasive wear. So let's dive in. You got some good pictures to show us, and let's dive right in.
When we start talking about corrosion, we'll talk about several things that have a potential effect or impact on it, and a couple of different types of corrosion as well. What most of us know corrosion as, Michael, is rust on parts. That's probably the most common corrosion type that we see. Right, rust on a car that maybe bubbles the paint up a little bit or something, or
Mm-hmm.
half the side of the pickup bed is gone, that sort of thing. It also causes problems on some internal engine parts and internal compressor parts as well. So being familiar with how to recognize it, and maybe a couple tips on how to abate that type of wear, or avoid it from progressing. And we'll talk a little bit about the types of failures that it can potentially lead to as well. All right. So when we talk about corrosion types, general corrosion, which is basically if you had a steel plate sitting outside and it was unprotected, meaning it wasn't painted or coated with anything, it would begin to develop a thin rust layer over the surface of it. That would be more in terms with what we would refer to as general corrosion. And what it takes is not just the steel or the composition of the material that's corroding, but also whatever we're potentially wetting it with. So we'll get into that a little bit, and then we'll also talk about galvanic corrosion. And this is an interesting one because it deals with what we refer to as dissimilar metals. Like a common one, I have an LS motor in my Jeep out in the shop, and it's an all aluminum block and aluminum heads, and I use stainless steel fasteners with it. So if I just put those stainless steel fasteners in and torque them without putting a dielectric grease between the threads, then I'll begin to develop galvanic corrosion due to dissimilar metals and the aluminum corroding and trying to bond itself to the bolt. So we'll talk about that a little bit, and then we'll talk a little bit about high temperature corrosion, and not a necessarily a true form of corrosion. However, it does do part damage and potentially affects performance issues and availability or uptime.
Let
So
me ask you a question about location and humidity. Is that, if you're in Houston on the coast versus where you are in Colorado, uh, how does that play a factor in general corrosion?
So humidity plays a factor. Ambient temperature, or the temperature that the component parts are exposed to, plays a temperature or plays a part in it as well. Not just the high humidity, but such as in Houston, we're fairly close to the ocean, and there's a lot of salt in the air, which salt causes that moisture in the air to be a more aggressive electrolyte on some component parts, causing the acceleration of the corrosion. Good question. All right. So when we talk about general corrosion, it's electrochemical activity. It's basically what's happening. Not to get too deep into it, but this is a piece of steel down here, and we have different grains in our steel. Our steel is made up of tens of thousands, if not hundreds of thousands of grains, depending on the size of the part, that are all bonded together, that consist of anodes and cathodes, is what we call them, and they have different electrical potential, meaning that if there's voltage in one and voltage in another, and one is higher than the other, all I need to do is bridge the gap between the two to cause current to flow. And when current does flow, then it reaches the anode area, which is we're bridging this gap between cathode here and anode, and this is anode area here, and it begins to oxidize the anode, producing what we typically see as a pit, or a pit inside of a pit inside of a pit as it continues to happen. But knowing that our different metals have different anode potential, there's a chart known as the chart of noble metals. When we talk about noble metals, we're oftentimes referring to the anode count in that metal. Like zinc is way at the bottom of that chart, right? It corrodes. It's got a very high anode count, very low cathode count, and it corrodes fairly rapidly. Where if we look at something like gold, you've seen pieces of gold that have been pulled out of the ocean that have been down there for hundreds of years, and they break the barnacles off them and it's shiny gold. It's not corroded. It was just something growing on the outside. So that would be more of the noble side of metals, which is going to have a lot more cathode than it is anode. So different metals corrode at different rates. Different electrolytes, what we wet that metal with, can cause corrosion rates to be variable. So some, such as the salt or potential gases in an exhaust gas stream in a natural gas engine, especially if we're combusting H2S in the combustion chamber, right? Very, very corrosive constituent. When H2S combusts in the combustion chamber, it's interesting that at temperature, it doesn't only generate sulfur dioxide, but it also generates its own water, which accelerates the corrosion. So now you've got an electrolyte plus the corrosive constituent. So when we see H2S related failures, boy, corrosion is pretty severe. It really likes to attack yellow metals such as copper and bronze alloys and things like that, brass. So with that being said, if we take a look at some pictures here, these are all crankshafts. We've got this is a 3500 crankshaft journal up here. I believe this was a 3400 crankshaft journal here, and an aerial compressor crankshaft here. And they all have similar damage. They all have pitting on them, but different degrees of pitting and some different coloration as well. So we'll start with this one up here, Michael. This is a crankshaft that just came out of an automatic parts washer in a rebuild center late on a Friday afternoon. And the way the story was told to me is somebody was asked to spray it down and cover it up so it didn't corrode over the weekend. So apparently the individual was not a service technician, but more of a kind of like a cleanup guy, I guess. So he went down there and he sees guys spraying parts down all the time, and with this Hudson pump up sprayer. So he grabs that pump up sprayer and he sprays the crankshaft down, covers it up. They come in Monday morning and it looks like this. Unfortunately, what he sprayed it with was a high concentration of the caustic cleaner that guys spray baskets of parts with that are excessively dirty before they push the start button.
Yeah.
So incredibly aggressive electrolyte, right? So the pitting on this crankshaft, if you look like in this area here, can you see my cursor?
Oh, yeah.
Some of those pits get pretty deep and basically junk the crankshaft because the pits are also down in the oil hole. And these pits become what we refer to as stress razors, that anytime we have pitting, especially in oil holes or in fillet radiuses, tough to grind out, especially in the oil hole. But those pits become stress razors, potentially leading to fatigue fracture. So that was an expensive lesson in what not to spray a crankshaft down with.
Ouch.
This crankshaft here on this engine, when we see this damage here right in the fillet radius, oftentimes that occurs when a unit is stored outside and not protected properly from outside elements, meaning that if it doesn't have any of the exhaust after treatment, such as a catalytic converter or catalyst or a muffler, then sometimes we'll see foil tape used or a type of tape used on that flat top exhaust flange. And we've seen it where a hailstorm will come through and the hailstorm will go through that aluminum tape, and now it's open, and now it can rain, and that rainwater gets in the exhaust manifold, looks for an open exhaust valve, and fills up the top of the piston area, and then runs down the side of the cylinder wall and drips right here on the crankshaft. So there's,
About how long does it take to start doing that type of damage? So I mean,
well,
if you
that's
left
a
it out
great
there on
question.
if you left it out there on a Friday and it rained on Saturday, could you come in Monday and get that wiped down and save it?
Oh, probably so. Yeah. So depending on how severe the corrosion is, when we see this type of damage here, I'm trying to think. We've done a few analysis on these over the course of the last few years, and I want to say they've been sitting outside for a year, maybe two,
Oh,
maybe
okay,
even as
okay.
long as 3 years, right? But when they pull this engine out of storage, if it's already been rebuilt or it's low hours, they don't tear it down completely. They do some checks on it, they change oils, they replace a few things, and they start going back together with it. Sometimes it gets missed that the exhaust was open and that we had water intrusion, right? But it drips on the crankshaft and it becomes the electrolyte that starts to corrode the steel. And then on this one here, this aerial crankshaft, we had water in this frame as well. So this bottom picture with the corrosion of this aerial crankshaft, we had water intrusion into the frame along with lubricant being present. And what we tend to see is with the water corrosion, you tend to see the pits like we do in this crankshaft picture to the right. When we have water mixed with the lubricant, it tends to leave a very dark or black surface. And the industry term for this is black acid etching. This is what lets me know that, hey, this thing sat for a while. There was water present in the oil and it corroded this area here. And notice how dark and black it is, Michael.
Mm-hmm.
So we also see stuff like this, like on anti-friction bearings, like tapered roller bearings
Mm-hmm.
that have had water mixed in with the lube oil. We'll tend to see the black acid etching there as well. And what it
What?
does, one thing we need to keep in mind is that anytime we damage the surface, we're we're also generating secondary debris. And that was the first podcast that we did on abrasive wear. So we need to ask ourselves, what type of damage could that secondary debris be doing elsewhere in the component? You know, if it gets into bearings or into divider blocks, or is it going to cause things to want to stick or wear at an accelerated rate, right? As well as when we have this rough surface against that soft bearing surface, then we start to generate the very aggressive two-body abrasive wear, or the accelerated two-body abrasive wear, like we talked about in the first podcast.
And what's that yellow material there? Is that oil?
This is oil. Yeah, it's
Yeah,
dripping right
okay.
here. Yeah. And then you can see the rust right down the center line where it's a no contact area of the bearing.
Mm-hmm.
It's important that when we assemble components that we wear gloves when we're touching bare steel surfaces, just simply because of the oils and the salt in our skin, which can be um, a whole lot worse than when we get into the deep South, places like Mississippi and Louisiana and South Texas. And the problem is that not only is it unsightly, like the rust and corrosion that you see here, it can generate secondary debris in the form of the iron oxides, which is rust, as well as potentially producing pits that can be stress concentrators or stress raisers that could lead to fracture later. What's that old term, Mike? An ounce of prevention is worth a pound of cure, right?
Mm-hmm.
Yeah. So just putting stuff together. Remember the first podcast we did with the wear types, we talked about cleanliness and the importance of that. I think we also covered that when we talked about engine and compressor bearings as well.
Mm-hmm.
So this is part of the cleanliness portion of it. So when we talk about how can I tell that it's corrosion? How do I know that it's not a different type of wear? How do I know that it's not a fatigue wear? Fatigue wear produces pits as well. Okay, well, when we look at the corroded surface, what tends to work well for us is we'll use a magnifier in the form of like a USB microscope and set it right on the surface of the pit. Then when we focus, what we'll see, and this is a picture of a large pit that's been magnified, and what we'll see is we'll see another larger pit here, another pit forming here inside of this large pit, another pit here, a big pit here with smaller pits forming inside of it. And if you increase the magnification, you'll actually see smaller pits forming inside of these because the corrosion is continuing,
Mhm.
right? So when we talk about, is it corrosion? Well, we teach, look at it closely. If you see pits inside of pits inside of pits, then it's corrosion, and you need to figure out why. Is it temperature related? Is it atmosphere related? Um, are you getting excessive amounts of liquids in a particular area that are acting as an electrolyte and potentially corroding a surface? So when we see the pits inside of pits inside of pits, it's a good telltale sign that it is actually corrosion. Now we just need to make a determination which type of corrosion it is. And you can do some of that visually, but when it comes to like the folks at ASM, American Society of Metals, they tend to be the authority on most of this stuff. They'll say there are rapid corrosion tests and slow corrosion tests, and basically they're taking a similar piece of the material and they're either elevating or reducing temperatures, trying to get the corrosion to accelerate, and potentially wetting it with the different electrolytes and stuff like that. So there are tests that can be performed, but they take a while. Even the rapid test is not as rapid as you would think. So, all right. So again, on the internal component parts, and when we talk about corrosion and the pits that it leaves behind, this is the side of a connecting rod. This should be a very smooth finished machine surface that should have a specific surface roughness. So if it bumps into another rod that's right next to it, that it's not going to cause any damage or any accelerated wear between the surfaces. So when we see these pits, well, this rod is made of steel. So as this pitted, it released secondary debris, again, in the form of iron oxides. And then when we have pits like this, they become considerable stress concentrators, stress raisers. We tend to see a lot of fatigue fractures start as some form of corrosion because the corrosion created the stress concentrator for the fatigue fracture to begin to initiate.
That spot where you've got highlighted there and it's showing some corrosion, that's near a bolt hole.
It is. So we're near one of the thinnest cross-sectional areas of the connecting rod, right? B, we're right near the bolt hole. So we also have some compressive stress here because of the bolt compressing those areas down. And then stress concentrators here. And we have seen things like this, as well as some other problems in these areas cause connecting rod failure, which inadvertently results usually in a hole in the block. So, all right. So the last type that I thought we'd discuss, Michael, is high temperature oxidation corrosion. And I guess a relatively easy way to explain it is the cutting torch. So if we're using an oxy fuel torch, we have some type of fuel, such as a propane or acetylene, and then on our cutting head we have the lever that we push down, which is the oxidizer bar. So if we just take that torch tip and put it right against the steel without preheating it and hit that oxidizer bar, it essentially does nothing, right? Wastes a little bit of time and oxygen.
Mm-hmm.
So if we hold it there and we let the molecules, the atoms in the surface of that metal, get a little excited because of the high temperature, they start to oxidize. And as they start to oxidize, we're introducing oxygen molecules into that area. Then we can flood it with a lot of oxygen when we hit the oxidizer bar, and it cuts the steel away, right? So if we were to just hold that without hitting the oxidizer bar, it's going to do considerable damage to that surface just because of oxidation and the heat applied to the surface, right?
Mm-hmm.
So we see this on potential on different parts in engines. In particular, this one comes to mind. So this is a exhaust manifold or a section of an exhaust manifold on an inline 6-cylinder engine. I believe that this was maybe a 3306, a G3306. And no, I take that back. This is actually a D3306. You can tell by all the black exhaust here. Again, I don't want the gas guys getting on me about the dirty diesel stuff, right? So what can happen is if we have excessively high exhaust temperatures, as well as potential corrosive constituents in the exhaust stream. So On the diesel side, high exhaust temperatures in here could mean raw fuel entering that exhaust manifold. On the gas compression side, we could be excessively high combustion temperatures or potential corrosive constituents such as H2S in the exhaust stream. So it heats this area up just like we did with the cutting torch, right? And it just begins to oxidize. And we've got a lot of airflow coming through there as well. That's almost like hitting the oxidizer bar, and it
Mhm.
damages this area. So this should be solid all the way across here. It should look just like this all the way across to prevent this exhaust gas flow from reverberating against this exhaust gas flow so they can both exit upwards into the turbocharger. This affects performance. Um, it's also an indicator of other underlying conditions, such as combustion issues or fuel issues or timing issues, things like that. So if we're wanting to prevent corrosion, and that's another conversation. So when we corrode, it tends to not be so much of a buildup as it is taking material away, right? If you think about it, as it oxidizes, the metal just goes away, and that's what causes the problems. So things that some takeaways that we could check off here would be coating of the parts. So if the part is painted or maybe potentially protected with a galvanized coating or some other type of coating, um, to keep the oxygen, keep the moisture off the surface of the steel.
Mhm.
When we use things like fasteners, such as a bolt, hard washers, and a nut, so corrosion can start sometimes because we have used an oil phosphate coated hard washer with a zinc dichromate bolt. And just simply the moisture that's in the atmosphere right at the crevice where the bolt head hits the washer, it can start to corrode in those areas, right? So keeping things oiled down, keeping things greased properly, making sure that that lubricants are not contaminated with any form of water, being careful when we do pressure washing on components, where that water's going, especially with a lot of natural gas engines. Sometimes the outside of them gets pressure washed before they start to do maybe a major tear down or something. And if the breather assembly on top of the valve cover isn't protected or capped, and we have potential for water going in that way, um, or even just during maintenance issues, right? Uh, Taking care of maintenance problems or performing normal maintenance. Um, the rainwater is something else to think about. If uh, if oil is leaking out of a gasket or seal, well, you can rest assured that dirt is going in. And if it's raining or it's snowing and the wind's blowing, then water's probably going in as well. So just some other things to think about.
All right. Well, thanks for putting together that slideshow for us and giving
Yeah,
us your input.
my pleasure. I hope the listeners can glean some helpful stuff from this. And
Yeah. And the watchers too. We'll put the link to the YouTube in the show notes so people can watch it too, because it's a lot more helpful to see the pictures as you're explaining it.
okay, perfect, perfect. So as far as corrosion prevention, the way that we handle parts, and I'll be sharing some pictures on our Facebook page here in the coming week of a couple of different Rexnord rotating coupler bolts, a new one and one that's been riding around in a toolbox of a field service truck for a while. That sometimes they get used. I mean, I'm hearing that from the guys, right? Sometimes you got to use what you got, and corrosion on those bolts potentially leading to bigger problems, torquing issues, fatigue fractures, coupler failure. So the way that we protect our parts as well, keeping parts clean, dry, oiled down if they're not in use or if they're going to be stored. So just a couple other things on corrosion prevention. And then a big one is operating temperature. Especially it tends not to be as much of an issue, except in cold climates, obviously. Um, if we're not maintaining operating temperature of the engine, meaning the coolant temperature, then we have the possibility of excessive moisture and condensation development in the crankcase without being able to boil that water off and then get it to evacuate out of the crankcase through the breather assemblies, right? So just a few things there that customers can potentially look for to help them diagnose their corrosion problems.
Cool. And if people want to find you guys online, is it just on Facebook? Is it Failure Analysis Services?
It is.
Okay.
It's Failure Analysis Services on Facebook, and it's Failure Analysis Training on Instagram.
Okay. All right. Well, great, Jim. Look forward to getting this episode out. Let everyone take a look at it, and then I guess we'll see you again next week.
All right, Michael, sounds good.
Thanks, Jim.
Thank you.